Hi, everyone. I'm here with Phani Paladugu, who is going to present this work. He serves as a product management executive director at Synopsys, where he oversees competitiveness of interface IPs for high-performance computing, mobile, automotive, and the consumer market vertical. He also oversees ecosystem partnerships and chiplet initiatives across business units. Before working at Synopsys, he worked in companies such as Rambus, Cadence, SmartPlay, and ST Microelectronics. So he has really extensive experience in semiconductors with specific focus on high-speed interfaces, memories, which include custom HBM, and also in security solutions. So, Phani, the floor to you.
Thanks, Mario. Hi, everyone. Today, I'll be covering enabling programmable performance, memory, and interconnect innovations for AI-centric data planes. So let me start with the agenda. Today, I'll be covering the AI revolution and the need for data processing, the memory technologies that can work with the AI, and the interconnect technologies that are very important for the AI workloads, followed by chiplet-based designs and future of programmable AI infrastructure and the next-gen technologies that are needed from the interconnect and the memory side. And I will conclude the session with a Q&A. The GPUs and CPUs are exploded. The primary limitation for the AI workloads is not coming from the compute power. It is mainly coming from the limitations of the memory and the interconnect throughputs. So if you look at the left side graph, the compute power is growing exponentially, and the memory bandwidths and the interface throughputs are not able to meet the requirements. So with that, what happens is all the standards are taking the quick churn. If you look at the graphs on the right side, so back in the days like DDR to DDR4, it took like many years to finalize the standards. And if you look at the curve right towards the right, like it is exponentially growing. That means all the standards life cycles are getting shortened because of the AI workload requirements. Not only for the memory, it's a similar case for the interface standards as well. The traditional networking architectures that are designed for the general purpose applications are not meeting the AI demands, and that limits the AI system performance. If you look at the top right graph here, AI model sizes are getting doubled every 3 to 4 months. That leads to multi-dimensional system design challenges. So you have to look at the performance of the system as well as the power requirements, area, and the latency requirements. All these different key parameters you need to address in this multi-dimensional system design challenges. So if you look at the bottom graph, like the compute power is outpacing the I/O and memory bandwidth requirement. In current scenarios, the compute power requires 3 to 4 terabytes of HBM and up to 1 terabyte of PCIe and Ethernet. So the AI workloads are defining the memory and interface data rate requirements. That's what I would like to conclude here. Okay, let me move to the memory interfaces. There are different types of memory interfaces are available out in the market, and each memory interface is suitable for a specific market segment. If you look at the high bandwidth memory, it is mainly designed with a high bandwidth and high capacity that is well suited for AI accelerator applications. And DDR, most of you are familiar with DDR for quite some time. And this particular memory interface is well suited for the server applications. And we do have a LPDDR interface that is mainly designed for mobile and edge AI applications. Let me get into more details of each of these interfaces. unlocking the AI performance with HBM4 and HBM3E. The HBM4 can provide up to 2 terabytes of bandwidth, and HBM4E can provide up to 2.8 terabytes of bandwidth. And each of these HBM devices are available in 4 stack, 8 stack, 12 stack, and 16 stack to get to the maximum bandwidth and the capacity requirements. HBM4 can provide up to 64 gigabytes of capacity. And when compared to HBM3E, HBM4 uses the 2K IO, that means a wider IO. So that helps to get a better power efficiency with respect to the HBM3E. So HBM4 can save up to 25 to 35% of power when compared to HBM3E. So next I'll be covering the DDR5, redefining the cloud and server computing with the DDR5. So DDR5 can provide a very high bandwidth. So the data rates of DDR5 is ranging from 6.4 gigabits per second to 8.4 gigabits per second. And the DDR5 MRDIMM data rates can go up to 8.8 gigabits per second to 17.6 gigabits per second. So this gets us a very high bandwidth. And if you look at the capacity supported by DDR5 is order of 64 gigabytes per chip. So this gets us very high capacity as well. So in addition to that, DDR5 is using a lower supply voltage of 1.1 volt supply. So that gets us a better power efficiency with respect to their predecessors like DDR4. And with a larger capacity, it enables us a higher memory density per module for servers and high performance computing, which is very important. And it increases the burst length, improves the data throughput as well. Okay, let me move to the next one. Empowering the edge AI and mobile innovation with LPDDR6. So LPDDR6 can deliver data rates up to 14.4 gigabits per second. The LPDDR6 can give us 30% power efficiency advantages with respect to the LPDDR5. So it can support the voltage scaling as well as advanced power modes that can help us to further optimize the power efficiency. So in addition to that, it also supports advanced ECC error correction features as well as RAS features, which are very important for automotive and AI workloads. LPDDR also supports the deep sleep mode and reduced standby currents, which are very key for edge and mobile applications. This slide concludes the various memory interfaces available out in the market, and HBM is more suited for the AI workloads. And as a backup, some of the applications, the LPDDR6 also is being used for the AI workloads. Let me move to the interconnect technologies or the interface technologies that are very key for AI workloads. I'll start with high performance connectivity with the PCIe. PCIe is a very key interface that enables a lot of high speed and high bandwidth connections between different modules. So the PCIe can be used to connect two accelerators, and PCIe can be used to connect the NIC card to the CPU, and it can also be used for the CPU to the SSD connections as well. So if you look at the PCIe standard, it started back in 20 years back at PCIe Gen 1, that is 2.5 gigabits per second, and now we are at PCIe Gen 7, which is 128 gigabits per second. With the AI workloads, PCIe Gen 7 is the latest node technology available, and that is meeting most of the requirements. And the PCIe standard is a scalable and flexible technology. So scalability means per macro, you can use 1 to 16 lanes to get the the bandwidth that you are looking for. And if you are not satisfied with the 16-lane configuration, you should be able to use multiple instances of 16 lanes to get to the bandwidth that you are looking for to match the compute power requirements. And the PCIe standard is backward compatible. For example, if you design with a Gen 7, it has to support up to Gen 1. So to make sure and ensure the backward compatibility is met. PCIe also supports like low power states. So whenever the data is not active and like you would like to move to the sleep modes, like you can leverage one of these low power modes, and that helps to save the power during the low power states. Okay, revolutionizing the data center architectures with the CXL. The CXL is built on PCIe infrastructure. The CXL is also like a high-speed, high-bandwidth interface that is mainly addressing the memory bandwidth bottlenecks in the servers. So there are three variants of the CXL interfaces. The CXL.io, which is a high-speed interface that enables the connectivity, which is an alternative to the PCIe. And there is another variant, CXL.cache. CXL.cache enables high-speed coherent memory access for accelerators and the CPUs. The CXL.mem. So this particular variant will enable us the memory expansion as well as the memory pooling and memory tiering, so which is very important for the AI workloads. The CXL standard is like optimized for the latency. This helps us to minimize the overall round trip latency in specific application use cases. Okay. Let me move to the next one. The AI scale-up architectures with the Ultra Accelerator Link. Ultra Accelerator Link is mainly designed for seamless GPU to GPU communication. It enables memory sharing and the synchronization. So Ultra Accelerator Link also is very high bandwidth, high speed interface. And it is like the protocol is trimmed to a certain level so that it is a lightweight protocol. And it significantly reduces the CPU overhead for AI workloads. The Ultra Accelerator Link leverages 224 gig Ethernet physical interface for Ultra Accelerator Link version 200. And it leverages the PCIe Gen 7 interface for Ultra Accelerator Link 128 option. The scale-up architecture is mainly like it enables the vertical scaling within the rack. AI scale-out architectures with the Ultra Ethernet. Ultra Ethernet is also very high-speed, high-bandwidth, configurable interface that delivers the unparalleled speeds to meet the AI workloads. Ultra Ethernet also leverages 224 gig Ethernet physical layer. And it is a lightweight and low latency protocol. It implements the intelligent congestion control for managing the burst traffic. So Ultra Ethernet is currently at 224 gigabits of speed. If you look at the diagram on the right side, Ultra Ethernet enables the connectivity between the racks and to the outside world. And Ultra Accelerator Link enables the connectivity between the different parts within the rack. Okay, so that concludes the various interface technologies that are needed for the AI workloads. So let me touch on a different topic, the chiplets and the chiplet-based designs. So if you look at the AI accelerators and the GPUs that are available out in the market, most of these designs are reaching the reticle limits. So when the designs reaches the reticle limits, it leads to like a couple of issues, like thermal issues. We need to deal with the thermal issues, as well as like that reduces the yield. So in order to alleviate thermal and yield issues, we have to explore different options. So the one option is like breaking down this the larger design into multiple smaller designs, wherein that minimizes the risk and like the time to market by reusing the proven the silicon solutions. So this also enables the accelerated scaling of system functionality at a cost-effective pricing. And some of these designs will lower the overall system performance, lower the overall system power requirements with an increased performance. And the chiplets also enables the shift left in the total design cycle, because we can repurpose and reuse some of the existing chiplets, so that will minimize the overall design cycle. So I would like to touch on some common chiplets for AI applications. There are various, the entire AI chip can be broken into like multiple chiplets, like a compute chiplet. For example, either it can be a CPU or GPU or ARM compute subsystem. That's one option. And the AI accelerator chiplet and the IO chiplets, like as I discussed earlier, we are using a different interfaces in the AI workload. So you can disaggregate the PCIe, Ethernet, and UAL into like the IO chiplet. Based on the requirements, you can move this IO functionality to different chiplets and leverage the UCIe, Universal Chiplet Interconnect, to interface to the main AI accelerator or the compute chip. Similarly, we can disaggregate the memory as well. So move the memory to a separate chiplet, and you can use the UCIe to interconnect the memory to IO as well as to the accelerator and compute chiplets. The chiplet design naturally align with the P4's vision for agile and high performance networking. So I would like to conclude my presentation with next-gen solutions for AI scaling architectures. As I mentioned earlier, we explored the PCIe Gen 7 interface for a high speed and high bandwidth connectivity. So as AI is scaling up further, then we have to move to the next-gen solutions in near future. So recently, the PCI SIG announced the PCIe 8 standard. I think it will be adopted starting from like 2027. The standard is in development currently, and a lot of customers are looking at developing the standard, and it will be like adopted by 2027. And the memory interfaces as well. Like currently we are using HBM4, and the next step is moving to the HBM4E in a year or 18 months. And then we will be moving to HBM5 by 2028. Similarly, die-to-die or the UCIe interface. Currently, most of the UCIe Gen 2 is at 32 gig to 40 gig, and we will be moving to 64 gig for UCIe Gen 3, and it will be adopted in 2026. In addition to the UCIe, there are like different 3D IO and 3D compatible die-to-die solutions are being explored, because when we reach to the reticle sizes, then we will be moving to the chiplet architectures, and there are like a 3D packaging and 2.5D packaging and 2D packaging. So based on the type of packaging that we are exploring, we have different options for the die-to-die solutions. And as we explored earlier, like the Ultra Accelerator Link, currently we are using 224 gig Ethernet interface for Ultra Accelerator Link, and it will be moved to 448 gig by 2027. Similarly, like Ultra Ethernet as well, currently we are at 224 gig, and we'll be moving to 448 gig by 2027. This concludes my presentation. Let's move to the Q&A session.
Thank you very much, Phani. So I wanted to ask you something, since it's not really my field, I wanted to better understand what's the difference between, and what are the advantages of custom HBM versus standard HBM?
Oh, this is really good question, Mario. So up to HBM3E, there is only a standard HBM. So currently for HBM4, there are two different options, like a standard HBM as well as the custom HBM. So standard HBM is a standard DRAM-based architecture wherein, like, if you have two SoCs, right? Let's assume a host SoC and the DRAM SoC. DRAM has a memory controller and PHY in it, in the base die, and the host has the same, like, HBM4, PHY, and the associated controller. The interface between these two SoCs and the DRAM and the host SoC is the HBM. In this case, there is a set limit for the power and performance, right? For example, like the HBM4 is a 2K IO, and it, like, we have to, like, interface both the sides like a 2K IOs. But if you look at the custom HBM, so we are trying to leverage the available UCIe interconnect out in the market. And in the base die, we are moving the controller to inside and, like, interfacing to the host SoC through UCIe. So that way it can minimize the overall latency between the two SoCs, as well as, like, it will optimizes the power, and it will optimizes the overall bandwidth, and it also optimizes the shoreline for the host SoC. So you have more shoreline, and that can be leveraged for other purposes.
Got it. Thank you very
So
much.
most of the hyperscalers and a few other lead customers are highly adapting to the custom HBM, wherein they have a control on their host SoC and how they can interface it to the HBM.
Got it. Thank you. Thank you very much. And another question I wanted to ask you is, you have been talking about chiplets, and obviously chiplets would lend themselves to have an open marketplace for offering different functionalities that then can be combined together. Do you think such a marketplace will eventually happen, and if so, when do you think more or less we're going to have something like that?
Okay, this is really good one, Mario. I mean, there are a lot of discussions happening around this, and from quite some time, people are expecting the open chiplet marketplace to be available. That can help, like, different vendors as well as, like, different customers out in the market to leverage that. But as you know, right, like, a lot of these customers have their own secret sauce. So that's where, like, the adoption is going at a slower pace. But with the UCIe standardization, I think we are moving towards, like, an open chiplet marketplace, but we are not there yet. So in my opinion, it will be happening somewhere between, like, 2028 and 2030. By that time, we will have more chiplets, the standard chiplets available out in the market that can be leveraged to shift left the overall design cycle.
Sounds good. Few years out, but it's
Yes.
not too far. Yeah,
Yeah, not too far. Not too far.
Yeah, and hopefully we'll see also some of these chiplets for packet processing being programmable with P4. That would really be great. Yeah.
Yes, that's right.
Okay. Thank you very much, Phani. I really appreciate your presentation and your participation in the P4 workshop.
Yeah, thank you.